Hello, let's try to briefly review what we have seen so far. So we discussed the properties of a probability measure. We have seen the definitions of a random variable, the distribution of a random variable, marginal and joint distribution. We talked about the different notions of independence and independency. And then we switched to stochastic processes with the goal of assigning measures on product spaces. And we did that by means of transition kernels. We also have seen some examples of random variables. And so now I have either two options. I could try to repeat today's theorem, which is not a bad idea after all, or I can just keep going with the material. Let me see. Okay, let's see the last theorem. Let's try to practice it again, because at the end of the day I have to remember this result is important. So this theorem generalizes the law of total probabilities, and it says the following. Consider K a transition kernel from the space E curly to F, to space F. So if we have this, then for x in E, kf of x, which is the integral over E f of y, k of x dy, defines a function kf in script E, in the set of kf, a function kf which is positive and immeasurable, and this is for any p in the sigma algebra F. Then we have that for any set b in script F, mu k p, which is the integral over b mu dx k of x dy, is it actually like this? Oh, this was for any f in F plus. And this thing, okay, no, I'm wrong. This is over F, and this is over E. So this thing defines a measure mu k on the space E, no, on space F, for each measure mu on E, yeah, for each measure mu on space E. It was a good choice to review this because I'm making many mistakes, and that means I didn't learn it well. For X in E, B in script F, these two things coincide, which means mu K of F coincides with mu of Kf, which more explicitly is the integral over E mu dx, integral over f of y k of x dy. And this is for any measure mu on E, and for each function f on the sigma algebra. Let's try to write it again without looking. So, if K is a transition kernel from space, how can I denote a space more quickly? Let's write it in this way, from to the space F. Well, no problem, let's skip the actual notation. To F, then, okay, for any X in E, Kf of X, integral over E, integral over F, yeah, of f of y mu k of x and dy defines a function kf which is measurable with respect to E plus, which is positive and measurable with respect to E, for any f plus. So again, for any p in sigma algebra f, mu k of p integral over E mu dx k of x dy, the k of x and b, yeah. So this p defines a measure mu k on space F for any measure mu on space E. Thirdly, for any x I don't know if I should write this thing here or just keep this thing, but in any case, mu k f mu of kf integral over E mu dx integral over f of y k of x and b or dy. Dove va a finire il b? define this, and this holds for any mu on the space E. And for any F. Okay, a bit better. Now let's go on with the proof. So the first thing we have to prove is that this thing holds for any F. So let F in F plus, we have that Kf x belongs to E plus, so it's positive, and but it's well defined and positive. Positive. Function name. Since the number k of fx is the integral of f with respect to the measure this one. So it's well defined and positive. Now we have to consider two cases to prove that it holds for any f in F plus. If F simple, I'm not missing anything, I think. Okay. If F is simple, meaning that f of x can be written in this way. Pi of x. So it's a linear combination of indicator functions. Then k f of x is the linear combination of these things here. Why? And what is this thing here? What is this? But in any case, this is immeasurable and positive because it's the linear combination of positive measurable functions which to x associate k of x and b. Okay, this is good. We are doing a bit better than last time. If f not simple, choose simple fn in f plus such that fn increases to f. So that kf of x is the limit of k of fn. Then kf is measurable as the limit of immeasurable functions. Now we prove 2 and 3. So what do we have to show for each measure mu? So we have to show that it defines a measure for any mu on here, and it is of this form. So should we fix this set before? No, we have to fix the measure. Fix mu on here. And define, yeah, we have to define the functional from e to r extended, no, from script f to r extended positive, such that L of f is equal to mu k, no, kf, no, to mu of kf. Then if f is 0, we have that L of f is 0. If f and g are positive measurable with a and b real numbers, we have that L of af plus bg is equal to mu of k of af plus bg and integrated by the linearity of the integral with respect to k, with respect to the measure, which would be blah blah blah. We can say that this, oops, you can say this. And again, by linearity of integration with respect to mu, which is basically the linear combination of the functions plus. Finally, given a sequence, what do we have to show here? That mu k of fn such that fn increases to f, then k of fn increases to k of f by MCT, a monotone convergence theorem for the measure k. And L of fn is mu k of fn, mu k of fn which does this MC by the monotone convergence theorem for mu. So first, okay, so we should do this and then this. Hence, by the theorem that characterizes the integral with respect to a measure, which is this one that we will write in a moment, there exists a measure mu on E such that mu of P is equal to mu k P, maybe, no, on F such that mu such that L of f can be written this way for any f. And taking as function the indicator p, this implies that mu of p is mu k of p for any p. The theorem is this one. So I don't remember it. Consider this space, let L from E plus to R plus extended. Then there exists a unique measure mu on E such that L of f is equal to mu f for any f. For any f in E plus. If and only if f is equal to 0, L of f is 0, given fg e should be e plus, right? Yeah. Then L of a f plus bg is a of lf plus b of l of g for any a and b in R given sequence, increasing, should be increasing, right? No, well, maybe it's not stated here, but it should be increasing. Okay. Let's continue. Just as a note, the Fn are chosen such that Fn is of this form dn composed with f, where dn is the dyadic function, dn of x is the dyadic or dyadic, I don't know how to pronounce it. The sum of should n no n 2 to the n I from k, let's say from 1 to n times 2 to the n k minus 1 over 2 to the n restricted on this interval here, k minus 1 over 2 to the power n, k over 2 to the power plus n, the indicator where n plus infinity. I should write this formula again and try to make an example with the graph, but I will skip it. And as a lemma here we have that each dn, each dyadic function is an increasing rate continuous simple function on R plus extended, and it increases towards x for any x in R. Okay. Here we have another theorem related to the one we saw, related to the proof of the previous theorem, which says that a positive function on the space E is immeasurable if and only if it is the limit of an increasing sequence of positive simple functions. Now let's define product kernels. Product kernels. The product of K and L is a transition kernel KL, let's call it KL, well, from E script E to G script G, such that KL f is the integral over E k of x dy L of y b, maybe. Well, here it was simply KL f equal to k of LF. Yes, for any f in G plus, which more explicitly can be seen as KL of B. Let's make it an arrow. I don't think it should be written in this way, but here is what I have in the notes. Shouldn't it be like k of x dy L of yb? I don't know. I think I'm becoming too sleepy to do things well, so let's just close like this. I know it's not a lot, but at least we reviewed the previous result and the proof. We did it a bit more smoothly than last time. So the next things that we will see are product kernels. We will try to review this and then talk about different types of kernels, and we will keep talking about kernels, and then we will move on to expectations. Okay, I think it's enough for today, so thank you for everything, and well, bye bye.